Hello everyone. Today we'll start another lecture which will be actually covering the same ideas which we discussed in the last lecture, which is TensorFlow variables and constants. But now I will be discussing more examples to solidify the concept which you have learned earlier by giving you some exercises, and we will solve these exercises together. In the last lecture we finished off with this example which you can see over here, which we studied last time, which is advanced slicing with combined techniques. So we covered this particular example already. Now we will be just doing some more simple operations on TensorFlow constants, how it works. So here you see we have this particular operation which is, we call it as element wise operation, and what it is doing is it is basically performing element wise additions, subtractions, multiplications and divisions. So here you see what we have done is, let us say we have defined one variable t1 and we have defined another constant rather t2, and these t1 and t2 are basically constants and they are actually the matrices of dimension 3 cross 3. So what we are doing now is we are actually adding them, these two matrices t1 plus t2, and then we are doing another operation where we are doing subtraction operation, then we are doing a subtraction operation, then multiplication operation, followed by division operation. So you see all these four operations which we are performing, it will be done element wise. So for example, when you are adding the two matrices, it will be done element wise. When you do a subtraction, it will be done element wise. When you will do multiplication, it will be done element wise. By saying element wise multiplication means this one will be multiplied with 9, this one will be multiplied with 8, this one will be multiplied with 7. So if you want to understand what element wise multiplication addition is, what actually is happening when you have 1, 2, 3, let us say 4, 5, 6, 7, 8, 9, and then when you are doing a multiplication of this with, let us say 1, 0, 1, 1, 0, 1, 2, 0, 2, then element wise multiplication means you are multiplying 9 with 2, you are multiplying 8 with 0, you are multiplying 7 with 2, and whatever results that you will get by multiplying these elements individually, you will actually fill the spaces in these matrices, because when you are multiplying a 3 cross 3 with another 3 cross 3, whatever elements that you multiply, like for example 7 is multiplied with 2, the answer is 14, 8 is multiplied with 0, answer is 0, 9 multiplied by 2 is answer is 18. So like this way you will do element wise multiplication, division, addition and subtraction. So let us see this in this particular example. So here you see in this particular example we have a matrix T1 which is a matrix of constant TensorFlow. So it's basically the constant tensors 0, 0, 0, 0, 1, 1, 0, 1, 1, and then another one is 1, 2, 3, 4, 5, 6, 7, 8, 9. So these two are actually matrices. So when to start this first, let me import the TensorFlow STF, and then we run this. So you can see now when you are actually doing a addition, it will be 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3. Like this way element wise it will do a addition, and then subtraction will also be in the same way. Here you see when 2 is subtracted from 0, it will get 2. 3 when subtracted by 0, you will get 3, and like this way you will get for subtraction. For element wise multiplication, you can observe that the first row is 0 in this particular constant matrix, and the first row in the second matrix is 1, 2, 3. So when you multiply the first row with the first row of the second matrix, you will get 0 as the first row. Similarly you can do the division. So this particular operation is basically element wise operation. Now what we do is we will understand another concept which is called as broadcasting. So in this particular broadcasting concept, what we do is, let us say you have a matrix which is basically given by 1, 2, 3, 4, 5, 6, and you have another matrix, or you can say it's a vector which is of dimension 100, 200 and 300. So once you have this type of situation, how will you actually add these two together? Because it's not possible. So mathematically it's not possible. So let me show you what I mean to say. it's basically a matrix which is of dimension 1, 2, 3, 4, 5, 6. So basically this is a matrix of dimension 2 cross 3, and then you have a vector which is of dimension 1 cross 2, and the elements of that vector are this. So what happens is, basically when you try to add these two together, mathematically it's not possible because it's a matrix, another one is a vector. But in Python it is possible to do it by doing the concept of broadcasting. And what it means is, basically what Python will do is, Python will try to compare the dimensions first and see which one is smaller and which one is bigger. So here you see the dimension of this matrix is 2 cross 3, the dimension of this matrix is 1 cross 3. So basically here you observe that this dimension is greater than this dimension. So whichever is the lower dimension, that matrix will be replicated in that dimension to become equal to the first matrix dimension. So here if you see, for 1 is less than 2, so what will happen is, we will actually replicate these elements in the first dimension, and that will be made equal to the same as the first dimension of this matrix. So what will happen is, internally, it will be expanded like this in Python, and it will replicate the values here. So once the values are replicated, now you add the two matrices together, and it's possible to do this. So this idea is called as broadcasting, and the answer that you will get is 101, 202, 303, then you have 104, 205 and 305. So this is the answer that you will get, and this particular idea of replicating the rows again or columns again to make both the dimensions compatible, that idea is called as broadcasting. The main thing that we have to see here is that the dimensions has to become equal. Whichever matrix dimension is less, that matrix will be replicated in that dimension so that it becomes equal to the dimension of the other matrix. So let me show you another example here. So this particular example, you see here the matrix is 1, 2, 3, 4, 5, 6, and the other matrix is this 100, and then you have 200. So here what is the dimension of this matrix? The dimension of this matrix is 2 cross 3. Here the dimension of the matrix is 2 cross 1. So you see now again in this dimension both matrices have same value, whereas in the second dimension this matrix is greater than this matrix. So what will happen is, this matrix will be replicated in the column dimension so that it becomes equal to the first matrix, so that addition can be possible. So now what will happen is, what Python will do is, it will actually replicate the values 100, 200, 100, 200 like this, and then it will do the addition. So what will be the answer? 101, 102, then we will have 103, then we have 204, 205, then we have 206. So you can see you will get this particular type of answer. So let me run this and show you the answers, whether they are indeed the same or not. So let me run this. So here you see in this particular example, you are exactly getting the same answer. This is 101, 104, 202, 205, 303, 305. Here also you are getting, sorry, this will be 306. It's not 5 because I have written 6 here. So it will be 30 plus 6, 306, not 5. So it will be 6. Then for the other case, as you can see here, this one I have explained. So once I run this particular code, let me see what answer I will get here. So answer that I am getting here is same as this one: 101, 204, 102, 205, 103 and 206. So this is the answer that we get when we add these two together. Let us take the another example, which is this one. So here if you observe, this particular is, or you can say it's a one-dimensional vector which is like this, and this one is basically a vector which looks like this. So here what is the dimension of this vector is 1 cross 3. What about this? It is 2 cross 1. So now what will happen is, you see in this particular case 2 is bigger than 1. So this matrix will be replicated 2 times in this dimension, that is In the first row it will be 1 2 3, and in the second row also it will be 1 2 3. Whereas here you have 3 and here you have 1. So what will happen is this is less than this. So this matrix or this vector will be replicated in this dimension 2 times, so that the final matrix that you will obtain will be of dimension 2 cross 3. So let us see how we will do it. So 1 comma 2 comma 3, then it will be replicated one more time, 1 2 3 as discussed, and then for the other one it is 100 comma 200, and then it will be replicated 2 times, so that the columns will become 3, 100 200 100 200. So what is the answer when you run this particular code? It will be 101 102 103, it will be 201 202 303 203. So let us run this and see whether we are getting the same answer or not once we run this particular case. So let us see here. So you can see 101 102 103 201 202 203, all of them are matching the results that we have discussed over here. This is the basic idea when you do the broadcasting. So the idea of replicating the rows or replicating the columns like this is basically the idea of broadcasting, and the main idea of doing broadcasting is to make compatible dimensions between the two vectors and matrices, so that you can add them together to get the result. So that is what broadcasting is all about. So if you so this particular session is on exercise questions. So if I say, like, I want to create a tensor of 3 cross 3 of ones and 3 cross 3 tensors of random values, how will I do it? I will be actually using tensors inbuilt function, which is tf.ones. So you can call this tf.ones of size 3 cross 3. So what it will do is it will actually generate a tensor of all ones, and the dimension of the tensor will be 3 cross 3. And if you want to do it for the random normal distribution, so what it will do is it will actually take samples from the normal distribution, and it will create 9. It will take 9 samples of it, and the reason why it will take 9 samples is because the dimension of the matrix that you are taking is 3 cross 3, and elements of these matrices will be 9, so that's why it's 3 cross 3. So let me run this, and after this you will see that for this particular case where you used tf.ones, what it is doing is it actually generating elements of this matrix all as ones, and you see the type also is by default float 32. So if you want to convert it into int, you have to specifically define the types here. So if you want this particular piece of code to be of type int 32, then what you have to do is you have to specifically tell that you need integer values. Otherwise, by default, it is float 32. You can see now, earlier it was float, now it is 32. So by default it is 32, but in case if you want it to be integer, then you have to specify it. Same goes with this particular example where these distributions are taken from the normal ones. Another basic question is that if you want to create a tensor like this, and if you want to compute the square root and square of the elements of this tensor, what you will do is actually you will define a tensor underscore value as tf.constant, which we have already done so many times, and what I am defining that is as float 32. And then what we are doing is we are squaring the elements of this tensor, and then you square rooting also for this particular tensor. So once I do tf.square tensor underscore value, then what I will get is I will get the square of these elements, and if I do a tf.sqrt, which is the square root of the values, then it will do the individual truncation of individual square root of these elements of this one-dimensional vector. So let me run this, and then you can verify yourself that the elements are indeed the square root of the elements of this vector. But one thing I want to point out here is that if I remove this particular piece of code, then you will see we are getting an error, because the reason for that is by default it is actually taking the value as integer. So here if I want to print the value of tensor, let me print this, print tensor underscore value. So let me print this and see what answer I am getting. So see here, by default this particular tensor is integer 32. So the reason why it is throwing an error is because when you do a square root operation, obviously square root results will be in all float, and we are forcing this value to be integer, so it's very difficult to calculate the square root of that operation. That's why we are getting this error. And if you actually comment this particular piece of code and then run, it will run actually. The reason for this particular piece of code running, see, this value is the earlier answer that you were getting, so it's actually storing that result in the buffer of this particular Google Colab, but as such this answer is not calculated because I have commented it, but still you are getting this answer. This is not right. The thing is, for this particular example, if you do this, it will actually calculate. But in case if you comment this and run this particular piece of code, then it will throw an error. And the reason for that is I have already told you that it will not be able to calculate the square root of the tensor because you are actually removing the d type as float. By default it is integer. So let me remove this, and now you are getting these answers. Okay, so this is regarding this particular simple exercise of creating the tensor and taking the square and square root of it. Now reshaping is again another very important topic. We want to reshape the vectors and matrices, and transpose is actually one of the special case of reshaping. So let us say if you want to create a 2x4 tensor and you want to reshape it to 4x2. So what exactly you are trying to do is you are actually trying to transpose it, because matrices, when you do a transpose means your row become column and column become rows. So here it is a 2x4 tensor and you want to reshape it. So it's very easy. You create a tensor of constant values 2, 3, 5, 6, 4, 8, 9, 10, and then you do a tf.transpose. This is our inbuilt function. So once you run this, whatever rows will be there, it will become the column. So here you see we have, for this particular constant tensor, we have 2 rows and 4 columns, but now it is 4 rows and 2 columns. So this way you can do a tf.transpose, which is actually a special case of reshape command. But let us delve more into the details of reshaping. So let us say you have another constant tensor of dimension 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a so these are all elements. Basically it's not a dimension. So here this particular constant tensor is having how many elements? This particular element, the number of elements in this particular one dimensional tensor are 9. So note that when you reshape it into another vector, the number of elements in that reshaped vector should also remain the same. So let us say if I have these 9 elements in the one dimensional vector, and if I want to reshape it, I will use this particular command, which is tf.reshape, and then what I will do is I will call this con1, which is the tf.constant vector, and I will reshape it into 3x3 dimension. So once I run this particular piece of code, what I will get is I will actually reshape this one dimensional vector into a 3x3 dimensional vector. One thing to note here is that in this particular tensor, it's a one dimensional tensor and the shape of it is given as 9, nothing is there. So this basically is very confusing to many of the viewers, because what exactly it is trying to say here is that the elements of this particular vector are 9. So number of elements in this vector are 9. It's not the dimension. So the number of elements in this vector are 9. So that's why 9 is written over here, and then comma, nothing is here in the on the second dimension. And this looks confusing because when you reshape it into a 3x3 vector, 3x3 matrix, you will get the exact shape as 3x3, which says that you have a 3 rows and 3 columns. But here it is if I go by this logic, it means you have 9 rows and columns are not defined. So this is very confusing. So in order to remove this confusion, what you can actually do is you can actually convert it into a proper one dimensional vector like this. So if you run this particular piece of code, now your shapes are properly defined, where you are saying it has a 1 row and 9 elements in this vector, and then you are reshaping it as 3x3 matrix, this particular vector. Okay, another example. So here you see we have, it's basically a three-dimensional matrix because you have three brackets. When you start with two brackets and end with two brackets, it means it's a matrix. But here it's a 3D matrix, and the dimension of this 3D matrix is 2 cross 2 cross 2. And now if I want to reshape this particular constant matrix, and what I want to do is, in order to reshape this, what I am trying to do is I am actually converting into a matrix, or you can say a two-dimensional matrix, where the rows I am interested in is to be having only 2. I am interested in rows to be 2, and I don't care about the columns. So if I don't care about the columns, what it means is rows will be 2, columns can be calculated automatically based on the number of elements that we have in this particular matrix, or you can say, tensor. So here the number of elements are how many? 2 cross 2 cross 2 is actually the 8 elements are there. So what I am saying is we have 2 rows, and then what you will do is this particular -1 indicates that adjust the elements, 8 elements, in such a way that you have 2 rows and then you have some specified columns. So the total number of elements in this will be, if I want 8 elements to get settled down in this particular matrix, how will I do it? I will be using 4 here. So I will be using 4 here. So if I run this particular piece of code, the dimension will be 2 cross 4. So what it means is that total number of elements that we have here is 2 to the 4 to the 8. So 8 elements are there in this particular 3-dimensional vector. And if I want to reshape it into a matrix having only 2 rows, then in 2 rows, how many columns should I have so that 8 elements can fit into it? And the answer is very simple. So if I have 4 columns here, then the total number of elements that we can have in that matrix will be 8, because 4 times 2 will be 8. So this is what here you have the reshaped vector, or you can say reshaped matrix of this 3D tensor. So you have to actually focus on the number of elements that you have. So the number of elements here are 2 into 2 into 2, which is basically 8. So by 8, and this how many elements are there? You have 8 elements, because 4 times 2 is 8. So let us see one more example here. So this one is basically it's also a tensor. So here you see, for this particular we have 3 cross 2 cross 3. As I have already explained you in the earlier lecture, these are batches and these are the dimensions of the matrix. So you have actually 2 cross 3 matrix, and then at the back side you have another matrix, and on the back side again you have one more matrix. That's why the dimension is 3 cross 2 cross 3. Now how many elements are there in this matrix? Number of elements here are 3 to the 18 elements are there. So now in this particular case, if I apply con 3 minus 1, so what I am doing is I am actually reshaping this 3-dimensional vector into a 1-dimensional vector, and I don't care how many elements are there. So minus 1 is basically, you calculate yourself what will be the answer, is what minus 1 is saying. So what it will do is it will actually convert this into a 1-dimensional vector of size 18. So it will be a 1 cross 18 vector in this particular case. Now in this particular case, what it is doing, it is saying that the number of rows are 2, and you keep the columns yourself in such a way that the answer that you get is 18. So in order to satisfy this particular equation, the answer that you will fill in here is 9. So here the dimension of the matrix that you will get is 2 cross 9. In this particular case, what it is saying that you keep as many rows as possible, but I want columns to be 9, but the answer has to be equal to 18. So in order to satisfy this, you have 2 rows to get this answer. Similarly here in this particular case, when you run this particular reshape command, what it says is you keep the first dimension as 2, I don't care about the second dimension, and then you keep the third dimension as 3, and then the answer should be 18. So in order to fill this particular gap, you know what it will be answer is 3. So the dimension of this matrix will be 2 cross 3 cross 3, because the number of elements will remain same in both the reshapes. So let me run this particular piece of code and see whether the matrix dimensions are indeed the same or not. So here you see in the first case I told that it's a 1 cross 18 dimension, so it's basically the same here. I will actually change this dimension again so that you will get more clear idea. Right now it is showing that it has 18 elements in it. It is not showing the dimension. In the second case, I told you that the matrix that will become after reshaping this tensor will be 2 cross 9. So here you see it's 2 cross 9. In the second case also it's 2 cross 9. So this is 2 cross 9. And in the third case it will be 2 cross 3 cross 3. So that is what here it is, 2 cross 3 cross 3. And all of them are integer by default. Okay, so the next topic that we want to discuss is tile command. And what exactly it does is it actually creates a new tensor by replicating the contents of the array multiple times. So like for example, if I'm using tf.tile in brackets, if I'm writing t means the content of that array or a matrix, and multiples means how many times you want to replicate it in columns or in rows. So the tf.tile command actually creates a new tensor by replicating t, that is the content of the matrix on an array, multiple times. So for example, if you see here, we have this tensor tf.constant with the value 1, 2, 3, 4. It's basically a one-dimensional vector. So what I am doing now is I've actually I want to actually repeat this content in the columns. So if I want to repeat this in columns, what I will do is I will actually write tf.tile t is basically the constant tensor which we have created for the one-dimensional vector, and then what I will do is I will actually pass the arguments 1, 3. So 1 means the row remains the same and the columns will be 3. So we will see what will be the output here, but actually once you execute this command, 1, 2, 3, 4 will be repeated 2 more times in the column direction. Let me run and show you to you. So okay, so now you see 1, 2, 3, 4 is repeated 2 times, like 1, 2, 3, 4 is the original one, and then it is repeated 1, 2, 3, 4 and then 1, 2, 3, 4. So it is repeated 2 times and the dimension of the new tensor becomes 1, 12. So here you see it's basically the dimension is increased and the columns are now 12, and you have repeated this content 3 times in the column direction. If you want to increase it in the row direction, then what you will do, you will pass the argument 3 here and then you keep the column as 1. Then what will happen is this 1, 2, 3, 4 will be repeated in the row direction like this. So basically it will be concatenation of the content in rows. So this is the dimension of the matrix will become 3, 4. Then we have, if I want to increase the content both in rows as well as in column, then what I will do is I will write 2, 2. So once I do that, it will be repeated 2 times in the column direction and then 1 time in the row direction. So you will have the matrix of dimension 2 cross 8. So this is the idea of tf.tile command. Another way of implementing that same function is through you write a constant tensor a like this, which we have already done over here, and then instead of passing the content here as 1, 3, what we have done is we have actually created another tensor, a constant tensor b, and then we are passing b over here. So effectively this particular piece of code and this particular piece of code are same, so you will get the same results. So this is just another way of implementing the same. So instead of passing the arguments directly here, what we are doing, we are actually creating the tensor first for this second argument and then passing it in the tf.tile command, which is this b here. So the next piece of function that we are discussing here is tf.expand. So the idea is to add a new dimension to the tensor shape. So the values of the tensor will not change. So please note, the values of the tensor will not change, but a new dimension will be added. So for example, here you have this temporary variable temp1, which is a TensorFlow constant defined as 3, 4. So if you actually initialize this temp1 with 3, 4, then if I print the original dimension of this tensor, this will be 1 comma 2. As you can see, it's a one dimensional vector. But now if I want to expand the dimension of this particular vector temp1, which is of 1 cross 1 comma 2, what I am doing is I am expanding the dimensions. So what I will do is I will expand the dimension at the 0th location. So you know that basically Python starts with 0 indexing. So we are trying to add the dimension at the 0th location. So if I add the dimension at the 0th location, so let me print the value of temp2 and let us see what its shape is. So you can see now the temp2 content will still remain the same. Earlier it was 3 comma 4. The same 3 comma 4 will be there, but now it's a 3-dimensional matrix. So you see here you have 3 brackets opening and 3 brackets closing, so stating that it's a 3-dimensional vector now. Earlier it was a 3-dimensional tensor, sorry. So here you see it's a 3 comma 4, it's a 2-dimensional matrix, or you can say 2D tensor. And the dimension of this particular tensor is 1 comma 1 comma 2. So what we have done is, so at the 0th location, I have added the dimension, which is now 1 comma 1 comma 2. If I want to add it at one location, then what it will be? It will be now 1 1 2. Why? Because now what we are doing is, we are actually adding the indexing at the second location. So earlier the dimension was 1 comma 2. Now I want to add the dimension at the first column at the first index. So now this 2 will be shifted to the third index, and now the dimension will be 1 1 2. Again, it's also a 3D tensor. Now if I want to add at -1 location, then what it will be? See, Python indexing starts from 0 till the end, and from the end, if I want to start, then from the end means if I want to start from the end of this particular array, the indexing starts at -1 and then -2, then -3, then -4, and so on. So this value 4 in this particular one-dimensional tensor is location 1. If I start from left, where the indexing starts at 0, and it's at location -1 if I start at extreme right position, and if I go towards left. So what I am doing now is I am actually adding the tensor at the -1 location. So it will be now 1 to 1. So this is the the new dimension of the matrix or tensor. This is the new dimension of the tensor, and you can see the content remains the same. However, we play around with the dimensions of this particular tensor, and we can use expand command for doing this. Let's see another example here. So here you see I have created a constant tensor of ones, and the shape of this tensor is 2, 3, and 5. And now if I want to and so basically by indexing, if you see, the 2 is at 0 location, 3 is at 1 location, and 5 is at 5 is at 2 location. Whereas if I start from right to left, it will be -1 location, this is -2 location, and this is -3 location. So now if I want to add the dimension at the 0 location, then what will happen is basically this will be the result. Because we are adding the dimension at the 0th location. At the second location, if I want to add, then it will be added over here. At the third location, if I want to add, then it will be at this position. And if the -1 location I want to add, this is equivalent to saying that you are actually adding at the last location of this particular one-dimensional vector. So basically you are actually adding over here. And if you are adding at the -4 location, means this is -1, this is -2, and this is -3, and then -4 is the beginning of the array location. So basically this is what this particular added dimension will be here at this point. So this is -4 location. So this is basically the way you actually expand the dimensions of the vector. And the important thing is the content of the tensor will remain the same. However, the dimensions will increase or decrease depending upon the command that we are using. So in this particular case, the dimensions are increasing. In the next piece of code, we will show how we can decrease the dimensions. So if you want to get the list of the dimensions, like here it is in the tensor format, If you want to get the list of this, you can actually use this particular piece of function, which is shape as list. So once you run this particular piece of code, what it will do is, use this it will actually use this particular tensor, and it will convert it into the form of list, which is given over here. So this is the idea of expanding the dimensions using tf.expand underscore dims command. So the next command is tf.squeeze command. What it does is it actually squeezes the dimension, and it's basically doing the reverse operation of expand dimension. And what it will do is it will remove all the dimensions of size 1. So if you have this particular tensor, which is tf.1 shapes 1 to 1 3 1 1 1, so it's basically a tensor of 6 dimension, as you can see over here. So if I want to use a squeeze function on this particular tensor, which has 6 dimensions, what it will do is it will remove all the dimensions of indexing 1. So if you use tf.squeeze command on this tensor, which has 6 dimensions, it will remove all the dimensions having size as 1, and then what it will result in is 2, 3. So let me execute this, and you see here. So once you execute this particular piece of code, you will get the answer as 2, 3. This is the shape of the tensor, which you will obtain once you use tf.squeeze command. So that's all for this particular session with this lecture, and the lecture which I had completed in the last session completes all the concepts related to TensorFlow constants. And I hope you got the good understanding of TensorFlow constants. In the next lecture, what we will do is we will actually go for TensorFlow variables, and we'll try to understand in deep what they are and how they are operated. And I will be actually uploading this file in my GitHub repository, and I will share that link down in my description section of this video. Thank you so much for watching this lecture. See you next time. Bye.